Our next speaker is Christian Gehring. He is a Senior Director of Robotics at ANYbotics, a Swiss robotics company building autonomous legged robots for industrial applications with a focus on high availability and reliability. He obtained his MSc and PhD from ETH Zurich in 2011 and 2016, respectively. During his PhD, he worked at the Autonomous Systems Lab supervised by Roland Sigwart. Thanks for joining us for our workshop.
Thanks for the invite. I hope you hear me. Maybe you can give me a sign if this is fine. All right, good. Well, yeah, it's a pity that I cannot be there in person. Really great conference and also workshop. I participated this morning as well. And so, yeah, let me introduce us, ANYbotics, right? We're creating a workforce of autonomous robots and believe that the plant operators in the future will not only hire people, but hire robots to get the job done. So you showed this slide this morning, right, that most robots today are using model-based control because they're working in very static structured environments, etc. And I hope my goal of today of this presentation is to provide you some insights about the real world problems that we are facing and sharing some use cases. I will also highlight some other aspects that are important to consider to achieve a successful adoption, right, of the technology that we have been discussing so far, especially for mobile manipulation use cases. So you will see our robots already run with learning-based methods in a second. In this video, I'll just show you quickly our robot and which type of environment it's working. So the robot is fully autonomous. It runs in various sites and does industrial inspection. So it has a number of sensors for navigation, but also for inspection. The environments are industrial settings, semi-structured, and the robot is built in a rugged way, so it can work outdoors and indoors environments. Pretty robust in these setups. There's always stuff moving around, so it's not really static environments. There can be people on site. The terrain is very challenging. There are stairs and steps. That's why you need a legged robot, right? And the robot can really work fully autonomously. It does navigation and path planning all on board. The robot also works in darkness, in areas where there's limited connectivity, and so on. So what we are working on is you've seen robots, right? They are massively deployed for manufacturing applications in industrial sites where it's more of a controlled environment, they're fenced and so on. And then we saw a couple of years ago, right? And the next revolution, so to say, in warehousing. So you have all these autonomous robots that are moving from A to B, moving stuff around. And we are going to revolutionize the next industry, the autonomous industry that are enabled by this AI-enabled robots in these more difficult areas and so on. So in this industry, people are working with a digital twin at the core. So they use sensors, for instance, at the first level of autonomy, they use connected IoT sensors to get data to feed that digital twin in order that they can digest the data and understand the health of their plants and so on. And they also have some limited motorized equipment, and the next level already started. So you have robots that are still, you need a human on site that operates and remote controls the robot, so it extends the human performance, so you can reach up higher areas, etc. But what our customers are looking for is ultimately autonomous inspection machines that instead of sending human people into dangerous environments, you can send robots that have all the sensing equipment to provide that information. But that's not just enough, right? Often something happens in these sites and you want to do maintenance work as well, not just inspection. So at the moment, we have all the technologies to enable this autonomous end-to-end robotic inspection. But what we are working on and building on is this closing the loop, right, with the real world from the digital side through manipulation. And the industries where these mobile manipulators are interested in for is for instance, metals. So you have steel manufacturing, aluminum recycling. Those are typically also indoors in halls, but pretty tough, narrow environments made for humans. Then in mining, where it's sometimes outdoors, it's pretty dirty around. Things are changing all the time. Oil and gas, you have offshore platforms where you don't want to have humans. Also in chemical plants, often you have explosive gases in the air. That means the robot is not allowed to ignite these, so you need to certify the robot equipment in order to prevent these explosions. And then you have power generation, where you have various fields, areas like wind offshore energy or nuclear power or gas power plants, etc. That's where we are deploying today our robots and looking into it. So the industrial environments are pretty, as I mentioned, quite narrow is one thing. There are steps, gaps, and so on. There's always stuff around. That's why you need legs. There are different ground properties, right? There's gravel, there are water puddles, etc. You have a lot of varying environmental conditions. So indoor, outdoor, there's lighting conditions changing. But not only that, right? Every equipment looks a little bit different, etc. And it's often areas where you really don't want to go, also for a short amount of time. So legged locomotion is basically manipulating ground reaction forces, right? So you have to deal with irregular terrain, and our robots are able to do that. You will see in a minute, thanks to AI, slippery ground. So you can look at the robot, right? It's basically a robotic hand with 4 fingers upside down. And you manipulate the ground, etc. And these capabilities, super robust, were enabled by deep reinforcement learning techniques. So today, and even 2019, we delivered the first RL-based controller to our customers that has been trained in simulation. So we have a neural network that basically coordinates all the legs and the actuators to achieve these high mobility capabilities of the robot. So they outperformed all the model-based controllers so far. What I think locomotion is a much easier task, and what you see with grippers, etc., because I think we can achieve satisfactory performance by only using geometric information, right? It's sufficient for navigation. I think even the use cases that we are looking at is where you really want to incorporate semantics as well for obstacle avoidance, etc. But for the fundamental manipulation skills or locomotion skills, RL does the job, so we can replicate the geometric space in simulation and train on that, and then do a sim-to-real transfer directly, and it works. What I believe is that there is a lack of abundant data for real-world applications for mobile manipulation. So current AI models trained on online and mostly lab data, they don't generalize well to our industries, to our world. So it's not just robot data that is missing, but also understanding industrial environments. I can show you 2 examples. So as you know, our robots climb stairs, and this is very important, and you need to make this really reliable, right? If the robot makes a mistake, it falls down, it will most probably be damaged, like us, we're getting hurt when we fall down the stairs. And so to achieve this capability, the robot needs to understand the environment, where to place these feet. So you need to capture with the perception system these stairs. But however, in these environments, in industrial environments, you have actually a lot of graded floors, metallic and reflective structures, see-through stairs, etc. Typically in our households and so on, we don't have these types of stairs. And if you look at how we get this information, how we make these mappings, is we use stereo depth estimation. So we have stereo cameras with actually active ones with IR projectors, right? You get 2 sets of images, and then you run like classical semi-global matching algorithms, etc., to create the depth match image. And unfortunately, these methods, right, they have their problems with this kind of environments. So you see a lot of outliers, you see reflections, and you end up with missing data. So if you look at these stairs, the robot does not know how to get down, where to place, because it has just missing information. So in the past years, there has been quite some progress on AI-based models for stereo depth estimation. So let's use deep learning, right? And if you look at those models, they don't work out of the box. So we compared the few at the Cray stereo that was trained on real and mostly synthetic data, and the NVIDIA model that is open source or that you can download and test that was trained on real data and also synthetic data. So if you look at these environments just in our lab, right, you clearly see in the middle of the ramp, there's the Cray has a hole in there, and there's missing data on the ramp for the lower model, etc. So they and also, if you look at another situation with these reflections, right? Again, you have a hole in the floor, you have missing data, you don't see the rails, so you fully, etc. So they don't work out of the box. So you need to fine tune them and optimize them for these environments. And these are just nicely trained models for a very specific task. Our robots, they do gauge reading, right? So they read pressure or temperature. And the way we do it is we use specialized deep neural networks with a classical pipeline, object detection, interpretation, and then use the train deep neural networks on synthetic and real data, and that works very well. Let's look at it if you use these large general purpose foundation models. Basically, it's a VQA problem, right? So here, just an example, we tested other models, right? If you ask what is the value of this gauge, well, it definitely says a wrong number. That doesn't work. If you look at other pictures, it's a bit harder to see, but again, it's a wrong estimation. And so we thought about what about reading a watch, right? So can it predict the time? And if you ask that, it's quite funny. Most of the models and most answers are 10:10 is the answer, 10 o'clock, which is definitely wrong in this picture. And if you look at, again, if you ask, like, what would you expect the price of this watch, it's fairly accurate. If you ask what is the name of the watch or the manufacturer, it's pretty good. And this is because it's trained on online data. And there, typically, you see a lot of watches that show you the 10 past 10 and so on. Just a little example. So which data is best suited for which purpose, right? That was one of the themes questions. And as you all know, we are working along the data pyramid from simulated data that is basically defined rules, right? So the physics that we use for locomotion training, and then the synthetic data that basically resembles the real world, and then eventually use real data. And the trend is to flip the pyramid, right? All the foundation models, imitation learning use real data, whereas reinforcement learning is happening mostly in simulation, and then you do transform that. So I don't have an answer for this, right? What is best suited? I think depends on the methods and so on. Ideally, collecting real data is difficult, but one thing that I think people don't talk about is about what about data for verification, right? And I'm not talking about checking the algorithm, but it's about checking the final system, the final product. And there's more like, AI regulations coming up, such as the European AI Act, that will require data for verification and transparency to prove that your system works. And how do you test and verify manipulation, right? Because real world testing is also very expensive. We do that a lot just for the locomotion. And so we run thousands of tests with a specific set of stairs and obstacles. We run 1 week reliability tests. We run 24/7 tests outdoor on a facility to ensure that the system works properly. And there you eventually want to test also on variety of environments, and you need to make sure that it actually works in the environment where you deploy it, right? How do you ensure that? So you also need data for this. And what we're at the moment focusing on, especially for locomotion, is that we are investing in simulators. We're using Isaac Sim to train the controllers, but also test. We're extending that to more, realistic and photorealistic environments, so to say. Let me show you some examples for manipulation. What are we looking for in these environments? There are typically doors everywhere. Not everywhere, but often you find a door, and eventually the robot should pass the doors to increase the site accessibility, right? So we did a research project with ETH Zurich together. There's also a paper now at CoRL presented. But if you look at the real world examples, right? So we can build this door, and this door is actually a dynamic object. So there's a locking mechanism that you often have with fire doors, etc. Then you find this funny, doors, a door in the door, and you need to also ensure that it works in these edge cases, or you need to press the button to open elevator doors and so on. And then in nuclear settings, you have even super heavy doors that you need to change the behavior to open these doors eventually. Another application or use case is to open doors for cabinets or panels to do inspections of electrical cabinets. And there are, again, right, people are opening kitchen doors often, but then if you look into the real world, you have this kind of doors that are also at different heights, with different handles, and some are really, really difficult, right? But this one, you need very fine, precise manipulation to push it and to open it. So you want to go through heavy doors, but also open very delicate doors. Another use case is taking samples. So humans go into the facility, take a bottle with them, and then they basically push some buttons, open some valves, and then attach the bottle, and then they get the liquid out of it, and then they bring it back to the lab for further analysis. That's a job that is done routinely, daily, etc. And this is something where our customers are looking for automation with a robot, right? So there's the IRA challenge that happened this year, and it will happen, I think, every 2 years. It's quite interesting. So it's the chemical industry that proposes some challenges, some tests where you can participate. One of them was this taking samples, but again, it's quite a simplified environment. So here you have one type of thing, and if you look at the real world, right, they look all a bit different. You have different location things. You have different types of valves and bottles. Often, sometimes very complex. Also, here it's another version offshore where you have to deal with some things. What you have seen in the past, right, at the DARPA Robotics Challenge, they put together this opening valve. At that time, people have been working on solving this problem, and the solutions were all that you had a human operator in the loop, and they did some template matching, so having a CAD model, putting it together so that the robot knows where the valve is, and then running some open loop control actions. I think today we have better methods available, but still it's a challenging problem because there are different types of valves. Some valves you just need to turn halfway until it's open, so you need to double check that. In different situations with different handles, when there's also this type of lever valves, etc. Where sometimes the robot needs to really adapt its full body in order to reach that valve. So it can be in very tedious locations. We talked about, and I think I heard this number, I'm pretty happy with it. So it overlaps with my observation, right? If you look at all the academic work, is about the average success rate is around 80% of the deep learned solutions from manipulation, but that's not enough for industrial applications. So the problem is not solved through real world adoption. So deployment requires typically 99.99% reliability, or in manufacturing even more. And this is about the quality of performing consistently well. And this includes various aspects. On one hand, you want to have the the hardware, that it's durable over the whole lifetime of the system, right? You've seen in the morning they talked about smoking hands. And then another aspect is robustness. So again, it can deal with adverse conditions, variabilities and uncertainties, etc. I think there the focus is clearly, I see that. And then also resilience, right? Some people say like, yes, okay, this technique comes out with some emergent behaviors that the robot can recover from failures, right? It cannot pick something, so it tries again and so on. But you also need to ensure that this works fully, right? That you can guarantee that works if something goes wrong. So if you open a valve and you want to take samples, but then you fail to close the valve again, then you will drain oil onto the floor forever. So you need to have a high success rate. So you need to detect it, that it went wrong, and then you can close the valve again, try again. So in academia, right, people mostly focus on repeatability. So that's the success rate, but then there's also, if you have different users and different environmental setups, this is another effort to do. So how can we collect informative data in the real world to work on these topics? I think one challenge that we face is that critical infrastructure has very strict regulations. So in nuclear, for instance, so there we need governmental initiatives. Often also our customers, they have very confidential sites, so you don't want to share, so you cannot even bring your mobile phone to take pictures. Because they don't want competition to copy their processes, etc. So that's also difficult. But what is also difficult is actually to capture all the negative events when things go wrong, right? Failures are super hard to capture. And what we are trying to do is, well, we deploy robots for simpler tasks, that is inspection, etc. Then we can collect environmental data automatically, but it's a slow and tedious process to get the permission to do these kind of things. That remains challenging. There's also a question about which sensor modalities, right? If you look at how human maintenance staff do their job, they often use a combination of visual, audible, and tactile sensing. So they check typically which pump to inspect by just listening to the sound, the one that runs makes noise, so they can check that one. Closing the valve, they look at the field of force resistance, and then they typically confirm the success rate by reading gauges. So it's definitely important to go beyond visual feedback for technology adoption. Another question is about how to solve the problem. Should we do it in hardware or software, right? And my suggestion is really go, and it's also our approach, go with realistic high-performance hardware. Because that will provide enough sufficient challenges for the algorithms. And we did that in the past as well, right? We built this high-performance series elastic actuators for accurate and precise torque estimation and control that enabled us a paradigm shift in manipulating in leg locomotion by running force control, enabled whole body control and model-based methods, right? And then we worked on other algorithms, so we came up with learning-based control methods. And that one, they don't need anymore this torque control. So there's a paradigm shift again to the position control, and you can eventually build low-cost hardware. So that's an end effect. I think I would still go this way, right? Use good performing hardware, solve it for real, and then we will see from there how we can get down with costs and work with shitty hardware. Another problem that I would like to raise is in these environments is restricted connectivity. We have computational constraints, so there's really a barrier, I think, to adopt large models today for mobile manipulation, because we have a lot of trade-offs. So the robot needs to have all the compute on board, and that means you trade off, right, between compute and memory and latency. So offshore, it's really difficult to run stuff in a cloud to make the ad hoc decisions, etc. Often what people don't understand is, yeah, you can increase the battery capacity and then you have more power available. However, the problem is actually the heat, right? So if you deploy robots in 55 degrees, to get rid of that heat is pretty difficult. So you need water cooling, etc., and that increases space and weight constraints, or needs even more. So adding a beefy GPU doesn't work for our use cases. And in fact, actually, as you should know, cellular telecommunication is pretty unreliable and does not scale well. I mean, there are so many sites available today that are not connected at all. Improvements in energy efficient hardware restoration are not that incremental, or are incremental, and are so running really these big models is not feasible yet. And I think also the model distillation that comes with additional performance loss needs to improve massively in order that we can deploy these models, these big models. But at least it's nice to see what's the performance limit of this model, what works and what not. So coming towards the end, so one last thought that I'd like to share is that functionality is actually only half the story, right? So when you're working on algorithms in research, it's about solving the functionality. This is still a hard problem in mobile manipulation. We try to make it as a community to create general purpose algorithms, right? For that, you're looking for data in the wild, right? How can we collect that? But again, it's, as I mentioned, it's tricky in terms of gathering sufficient amounts of and sharing it also with third parties. It's not so easy, even though I would love to push that further. I think that helps a lot, and it's a great start to share lab data. The question is if this is really enough. But then when it comes to building applications, right, make it work in real life, you should also consider not just the operation lifetime of the product or the system, but also the deployment and development side. So we talked about reliability, but also safety is important. You cannot damage equipment or harming people. That's not acceptable. So you need also to prevent that. And then what is often forgotten is the usability. So how do you deploy it, right? So when we select algorithms, we always need to consider the usability and the deployment phase. So you need to wear a lot of equipment. It's very loud environments, hot. You don't want to spend time in there. And so and typically it's domain experts that will deploy the robots because they know what needs to be done, right? Not roboticists. So eventually our customers, our use cases are about no site adaptation and really spend only a few hours, not 20 hours in manipulation and collecting data for imitation learning. And then for the development, it's the fourth priority is kind of cost. So yes, we can build up some mock-ups in the lab, etc. But again, it's costly to post-train, fine-tune, and the question is whether we can actually bridge that reality gap. With this, I'm at the end of my presentation. I hope I could provide you some new insights on the problem from real-world perspective. There's not only pick and place and assembly or household task in the real world, but these are exciting times, and I'm looking forward to the next generation of learning-based algorithms to solve mobile manipulation in the wild. Thank you.